Hello, in the last lecture we learnt about the radial basis functions. So, let us extend the idea of radial basis functions towards networks. Okay. So, how do we sketch a radial basis function network and what are the typical ingredients? We have an input layer, we have a hidden layer, we have an output layer, but this network is not typical to what we think about having a neuron as a computational unit. There are some differences and we will see this as we get into the details. The input layer consists of M naught source nodes, where M naught is the dimensionality of the input vector x. So, M naught is the dimensionality of the input vector x, and the hidden layer consists of the same number of computational units as the size of the training samples. This is typically in a typical radial basis function network, the number of computational units in the hidden layer is the same as the number of training samples, but this need not be the case because it will be computationally intensive. But let us suppose that this is true and then we will proceed, and then later on we will arrive at a simplification to this step. Now, each unit is mathematically described by a radial basis function given by phi suffix j of x to be this function phi of the norm of x minus x j, right. The center is the data point itself going from 1 to n. Now, we can think about having this distance metric between every data point and the center. In some sense you are computing the pairwise distance across all the points. Now, there are no weights connecting the source and the hidden nodes. In the multilayer perceptron you could have weights connecting the source and the hidden nodes. In this case it is not the case. We have an output layer, and the output layer is a single computational unit, and there is no restriction on the size of the output layer, but typically the output layer can be just one, right, just having one node there. Now, the computational units are essentially these phi functions, and assuming the Gaussian function, we have this in this form, which is exponential minus 1 upon 2 times sigma j square, the norm of x minus x j square. This is the form of our function phi j, and since we assumed that the number of units in the hidden layer is going to be the same number as the number of data points, this goes from j equals 1 to capital N. Now, if we go one step further into sketching the architecture that we want given our ideas. So, this is how it would go. We have a set of inputs in an m naught dimensional space x 1 to x m naught, and we just combine them in a way to each of these hidden units, right. There is no weights, there are no weights connecting, it is a direct link with a value of plus 1. Now, in this phi 1 so on till phi n, we have these Gaussian units, and we discussed in the previous slide that this is how we would have the form of any phi j, right, and that is what we are going to have here. Now, the hidden nodes and the output are combined using a set of weights, and we denote them W 1 through W n, connecting the first node through the nth node of the hidden unit, right, of the hidden layer. The nth node of the hidden layer is connected to the output via W suffix n, and the first node is connected via W1, so on, and at the output we form a linear combination of this. Now, one has to know that this is not like a traditional neuron where we have an activation function over a local receptive field. So, this is a key difference between the RBF unit and the typical McCulloch-Pitts neuron that we have seen earlier. Okay, so, this is a basic sketch of the RBF architecture, and if you are savvy you will see that the key thing in the learning process is learning these weights, and these weights are learned during learning as part of the optimization procedure, because we know what we get at the output of the RBF network and we know what the desired response is. Based upon an objective function we can optimize these weights, and we saw that sometime earlier that we can get these optimal weights using the inverse of this phi matrix times the desired vector, right. We will invoke the same steps here. Now, how can we evolve a hybrid learning procedure for the RBFs, for the radial basis function? The idea is as follows: we obtain the hidden layer elements, that is the centers in each of the computational units, through a clustering algorithm, right. We are given a bunch of data points, and from these data points we arrive at some clusters capital K, which is significantly less than the number of data points capital N to start with, right. That is a key distinction, because otherwise I would increase the computational complexity, because I will have a lot of hidden units, right. I can reduce this complexity by using clustering, where I can choose k clusters that represent in some way these n data points under some distortion measure. And then the next step would be to solve for the optimal weight W, linking the hidden layer and the output layer. So, the only unknown are these weights W that we have to solve given the set of data points, and the k clusters which have to be chosen appropriately. Now, here is a sketch of this hybrid learning algorithm. The input layer has inputs of dimension m naught, right. The size of the input layer is determined by the dimension of the input, and the hidden layers, they comprise of a number of Gaussian units or these radial basis function computational units, and the number of units are determined by some clusters, which is a trade off between the performance and complexity, right. You do not have to have capital N number of such units as I discussed earlier. So, therefore, you have a computational reduction, and that would have some trade off in the performance, because ideally if you choose every data point as the center, your distortion would be really less, right, but you sacrifice the distortion with complexity. Now, using an algorithm such as the k means algorithm, we can obtain the cluster means mu j hat here, the hat indicates it is an estimate, j going from 1 to capital K, because we have k such clusters, and this is based on the inputs that we have xi, I going from 1 to n. And then we compute these phi j's using these cluster means over all the data points, and once we have these computations done and a phi matrix formed from these points, right, that is we have data points and the clusters, and with this evaluation we can form a matrix and we can combine those along with the weights and the desired response in the form of a matrix equation and then solve it. Now, one of the questions is, how do we choose sigma for these Gaussian units? One way is to have a sigma j, that is for every cluster I have a mean and I have a variance, cluster variance, and I can compute that sigma j and I can apply it. But this can lead to a peaky or a flat Gaussian distribution, sometimes depending on the centers. One way to circumvent that is to choose a sigma that is the same for all the Gaussian units, and that can be based on d max upon root of 2 times k. This is a heuristic, it is an empirical rule. And this d max is basically the maximum over I j, the distance between mu I and mu j, right. If you have cluster centers mu I and mu j, I mean the hat, because it is an estimate, we can compute the pairwise distance over all these cluster centers and pick the maximum, and that would be our d max, and k is what we know by virtue of our design parameter, and we can choose a sigma like this. So, this choice will ensure that the individual Gaussians are not too peaky or too flat. Now, once we compute these parameters, then it boils down to solving this matrix equation phi times w hat is this vector d, where d is the desired vector, and this phi matrix is formed over all these points I equals 1 to n over the clusters mu 1 hat through mu k hat. Okay. You may wonder at this step that phi could be a rectangular matrix, right. It is a square matrix if the number of functional units is equal to the number of data points, right. Then I also goes from 1 to n, j also goes from 1 to n. So, therefore, you will have a square matrix. It is not the case if data points go from 1 to n and the number of cluster centers we have are from 1 through k. In such a case, you will have a rectangular matrix and you will have to do a pseudo inverse computation to get the optimal w hat. And the direct inversion is difficult. In such cases, we circumvent these problems using adaptive algorithms, and one such procedure is using the recursive least squares algorithm, wherein we can solve for these weights optimally. At this step, we have not discussed the algorithm for clustering, and let us discuss how this clustering can be done. And the procedure is the k-means algorithm, which is sort of well known, and it is a very popular algorithm in the machine learning community. It is one of the very basic or fundamental algorithms that one comes across. So, what is k-means? K-means is a simple idea for clustering. It is unsupervised in nature because there is no desired response. I give you certain data points, I have to cluster them in some sense. In what sense do I cluster them? I need to have an optimization function for that. So, let us state the goal of the k-means clustering algorithm. Given a set of n observations xi I going from 1 to n, find a code book C that assigns these observations to k clusters in such a way that the average measure of distortion is minimized from the cluster mean, right. What it means is I am given a set of points and I have to have a label for these data points. So, imagine I have a set of points here, these are like this. So, naturally I can form 3 clusters here, and instead of representing the cluster through individual data points, I just have one label for each cluster, and that should be typically the cluster mean indicated by these blue crosses, right. In some sense it is like a code book. I give you a data point and it will give me the cluster center which it is associated with, or the index, and I can use this for whatever I want. And this is the basic idea behind vector quantization, and people in the signal processing community treat this as vector quantization. People in the pattern recognition or in the neural networks community or machine learning community treat this as a clustering algorithm, but they are one and the same. Now, the cost j of c is given by this distortion function. So, what it means is simply the following: we have k clusters, that is j going from 1 to k, we have k clusters over which we have to compute the cluster variance or this distortion, and for every such cluster I will have a data point xi which will be encoded to this cluster j, right. That is where this inner summation comes. So, this is basically computing the cluster variance or the total distortion across all the clusters, that is computing the total distortion over all the clusters. Now, how should we go about this problem? There are 2 steps. We have to compute this mean mu j here, and then we have to update the code book. There are 2 steps. So, let us see how we can go about doing this. Before we get into the details of the algorithm, the 2 steps, you may be savvy to observe that there is no scale factor n suffix j, where n suffix j is the number of data points that belong to cluster j, right. It does not have this cluster, it does not have the number of points for the cluster, except for that it is a measure of the overall cluster variance. Now, let us formalize this approach to solve this problem, and the idea is to use a familiar gradient descent approach to minimize the distortion function. So, the first step is as follows: for a given code book C, so you have to start with some initialization to start with, right. You may choose some random centers and then proceed towards updating it. The total cluster variance is minimized with respect to the assigned set of cluster means, that is we have to choose these mu j hats that minimize this cluster distortion. And how do we choose these mu j hats? From our familiar gradient descent approach, right. The mu new is mu old minus some alpha times the gradient of that cost with respect to the parameter mu, right, and we continually keep updating it. This is one way to do this, else you can directly take this functional, take the derivative and then solve for this optimal mu j, but we would like to do it adaptively because it is easier than doing the direct steps. Now, once we obtain all these mu j hats, j equals 1 to k, because we started with our intent to have k clusters, we optimize the encoder to choose the label I for a data point which is minimum over all, we have minimum over all the distortion functions, right. So, I give you xi is a data point, we compute the distortion xi minus mu j hat over all j from 1 through k. Once we compute that distortion, we pick that value of j that gives the closest distortion for the data point xi. That is, the code for the data point xi would be that point j star, which is going to be the least of the distortion over all the j from 1 through k, right. This is sort of implied. So, what it really means is we take this data point, we give it to all these clusters, and whichever gives the least cluster distortion, we assign the data point to that cluster, and we iterate steps 1 and 2 until convergence. Why that is iterative? Because we have not solved for these optimal mu j hats for j equals 1 through k, and we are adaptively estimating these cluster means, and that is the reason why this is adaptive, and we have to iterate between these two steps until there is convergence, where we see that this is the distortion that we will end up with, and we cannot go lower than that distortion. And you may ponder about this when capital K heads to n, that is, you choose all the data points, there is no clustering here, right, then there is a distortion which is 0, and this should be very obvious, and that is the reason why you have a performance complexity trade off in the RBF network, where you can choose k number of hidden units as opposed to all the data points themselves, and this is a more practical approach than having all the data points themselves as the centers of the Gaussian units. With this, we have completed the ingredients for the radial basis function network. There is one important step, which is the recursive least squares algorithm for computing these inverses efficiently, because we have not solved for the weights, right, and those weights can be done using a direct approach where you invert a matrix and then compute it. Else we can think about an adaptive algorithm that can serve this purpose. Okay. So, as we are here going through this equation, which is phi times w hat equals d, and we said that solution of w hat can be done using the inverse of this matrix phi, which is the Gram matrix phi times the desired vector d, and this can be done using an adaptive algorithm. To set up the adaptive algorithm, let us slightly delve into a little bit of the details through our notation, right. So, following our earlier notation, we have phi transpose of xi is phi of xi comma mu 1 so on till phi of xi with mu k. That means, we have all these k means that we have k cluster centers that can be done through some clustering algorithm, and I will discuss the k means algorithm following this as a way in which you can realize these clusters. So, I can compute phi of xi comma mu 1 dot 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 till phi of xi comma mu k, and that is my vector phi transpose of xi. So, phi transpose of xi times this weight vector is d sub phi, which is a scalar, and this vector is basically these weights W1 so on till Wk. Just note that phi transpose is this row vector and W is this column vector, and therefore this inner product is a scalar which is di. Now what I have to do is pre-multiply this equation phi transpose xi times this vector W equals di with phi of xi on both sides. That is, I pre-multiply equation 1 with phi of xi on both sides and I sum this over all the data points. What happens is pretty simple, straightforward. We have phi transpose xi which is pre-multiplied by phi of xi. I sum this I equals 1 to capital N times W equals summation I equals 1 to n phi of xi times di. Right, di is a scalar and this phi of xi is a vector, so therefore I can take in any order I want. Here I have to be careful because I have to pre-multiply appropriately. Now this summation is only over phi and not over W. So let me indicate this summation I equals 1 to n phi of xi times phi transpose of xi as this matrix R, capital R. So this matrix capital R times this weight vector W equals this vector small r which is given by this quantity on the right hand side of this equation. So this is small r vector. So let me call this as equation 2. Okay. So the right hand side of equation 2 is this vector which is r, and if you are confused I will put this in red so that it is sort of clear, and this quantity is this matrix R. Okay. So now we have capital R times the weight vector W equals this small r which is a vector. Therefore W, this weight vector, is capital R inverse times small r which is a vector. Now as you can see through this equation to compute the weight, let me call this equation 3, you will need the inverse of this matrix which is capital R, and this can be pretty hard if we have different or a large number of data points, and if n becomes capital N becomes quite large, then computing the inverse is going to be a hard problem. So or even the pseudo inverse, because if it is a rectangular matrix then still you will have to do something to get the pseudo inverse, and then computing that also becomes pretty hard. So in that context we will have to evolve a solution to do this adaptively, and for this we will adopt the recursive least squares approach towards solving this matrix equation. So in the next lecture we will discuss the recursive least squares algorithm, and we will talk about the details how this can be also done in an adaptive manner more efficiently. With this we will close this lecture. Thank you.